This is my brushless motor driver that's controlled using CAN bus. The joystick is connected to an STM32, which relays the position information over CAN bus. It also uses this joystick information to drive a NeoPixel display. The motor is powered by a USB brick. I use a 20 volt trigger in order to get 20 volts out of the USB brick. This 20 volts is fed to the full H bridge. This proves a simple way to have a reliable 20 volt source. Here we have the brushless DC motor driver board. It contains a full H bridge and some analog circuitry. It sits on top of the STM32H7 CAN nucleo board. The firmware for the STM32H7 is written from scratch by me and is developed using STM32 IDE. The velocity and the direction of the motor is controlled with the joystick. It uses CAN bus that comes from the joystick controller. It uses an off-the-shelf CAN transceiver and is connected to a CAN dongle so that you can see the signals on the laptop. You can also see the joystick position with the NeoPixel display. When I look at the CAN bus signals in PCAN Explorer, PCAN Explorer lets you visualize CAN bus signals, and the signal that I'm going to show is for the motor feedback. This is the motor property signal. This signal is used to display the RPM of the motor duty cycle, the temperature of the motor driver, and some other things pertaining to the motor. You can also see the motor control signal. This signal comes from the joystick. It's used by the motor driver to know the direction and the speed that the user wants the motor to spin. You can see how it responds whenever you have the joystick moving. I'll now show some of the signals on the oscope that are used to drive the motor. These signals are generated from the STM32H7 and used to drive the H bridge. These PWMs are generated from the timers within the STM32H7. I use these timers and PWMs in order to generate 3 sinusoidal signals. These are used to drive the 3 motor legs according to the rotor position. Here I'm holding the motor shaft stationary. You can see the low side and high side PWMs that I'm generating. In order to regulate how much current is going into the motor, I use a programmable dead time. When this dead time is large, there's limited current going into the motor, and so the torque is low. When this dead time is very low, it means that there's the maximum amount of current going into the motor and we produce the most torque. You can see how these signals change over time whenever the rotor is allowed to move. Usually you want this PWM frequency to be as high as possible. If it's low, then you'll be able to audibly hear the switching noise. Unfortunately, this motor driver board doesn't support high frequencies, so I have to have the frequency quite low. This is because there's a lot of capacitance on the lines and the motor driver board is pretty cheap. Right now the PWM is running at a frequency of 5 kHz. If you look closely at the oscope capture, you can see how the phases of the PWM are out of phase by 120 degrees apiece. If you look at the high side and low side signals, you can see that there's dead time built into the low side. Timer 1 is used to drive the high side, and timer 8 is used to drive the low side. Timer 1 is used to start timer 8, so the timers are perfectly in sync. Timer 8 uses the AND mode in order to create the dead time. All we have to do is set the compare register 5, and that's used to AND all the signals. In order to commutate the motor, you must know the rotor position. Luckily, this motor comes with an encoder built in, so we don't have to do a sensorless algorithm. Timer 2 is set in encoder mode, and encoder sides A and B are fed to this timer. When the encoder moves, the waveform is used to count the timer up and down. I use the 0 pulse of the encoder in order to zero out the count register. This fixes the problem of encoder drift and synchronizes the encoder to the rotor. And now that we're using the encoder to know the rotor position, we can now commutate the motor. All we need to do is just lead or lag the sinusoidal waveform. That'll cause the rotor to spin. Here you can see that the 0 signal of the encoder can be used in order to calculate how fast that the rotor is spinning. When the motor is spinning slow, this time is long. When the motor is spinning fast, this time is short. This is how I'm calculating the RPM of the motor. This is an easy method to drive a brushless DC motor. It gets more complicated whenever the motor is sensorless and whenever you use FOC in order to calculate the ideal waveform.